Today's rough cut series. I'm Rick Reddy. I'm the Associate Director of the Industrial Systems here at MSU. So thank you for coming. Got a very full room today, which is very nice. Thank you to those of you who are tuning in online. First, before we start with today's seminar, I want to announce that our monthly happy hour is coming up, and we've decided, in keeping with last month's precedence, to have it on the first Friday of the month. So it will be a week from Friday, or you can think of it as the first Friday after the first Friday of the month. So that will be next Friday at Bridger Brewing, 5 o'clock. Today we're very pleased to have Ben Poulter come and give us a talk with his colleagues. Ben is an assistant professor in the Department of Ecology here at MSU. He's been here for about a year and a half. He got his PhD from Duke and has had postdocs at the Potsdam Institute for Climate Impact Research and the Swiss Institute for Snow, Forest, and Landscape Research and the Laboratory of Climate and Environmental Sciences in France. And his research is on vegetation dynamics and the role that vegetation plays in carbon and nutrient cycling and climate change. So I will hand it over.
Okay.
Thank you very much, Ben.
So thanks everybody for coming. Okay, I didn't listen to your instructions about the clicker.
Oh,
but just use the mouse. Okay. All right. So about a year and a half ago, I gave a rough cut seminar that kind of presented some ideas that we had in terms of how we can use ecosystem modeling to address climate, land use, and disturbance impacts in the GYE. And so Kathy asked me over the summer, or at the end of summer, to give her another presentation in the rough cut as kind of an update to show what we've done over the past year and a half. And so the way that the seminar will work will be that I'll kind of give a very kind of like a 10,000-foot view of where we are with the research and the research projects, and then turn it over to the people in the group who are doing a lot of the work. So first, just want to acknowledge some of the funding agencies that are supporting the research in the group. Also, some of the model development teams. We're using several different ecosystem models in the group that we'll talk about today. Also, the support that we're getting from the research community, for example, Paul Lovett and Jerry Sheehan, who have been instrumental in setting up the networking and computational infrastructure that we use. The data providers, just an example of some of the data sets that we use in the group, and some of the main collaborators and consortiums that we're involved with. And so collaborations extend across the globe, which is fun if you like beer. So this is a map of people's favorite beers by country. So within the group, the Ecosystem Dynamics Lab, we have a lot of different projects going on. And I'll show in the next slide kind of how they tie together and what the overarching question is that links this work. But two of the big projects are based on global scale carbon dynamics. One is associated with trying to close the global CO2 budget, and the other is looking at now the global methane budget and trying to come up with bottom-up and top-down reconciliation of global methane fluxes. And then within these larger projects, we have work related to RED+, and trying to estimate tropical biomass within a functional commercial service that could be used at the project level, and then also evaluating climate change impacts on forest, tropical forest dynamics. We're also looking at semi-arid systems, in particular looking at climate vulnerability of sagebrush systems in the West. And then we have several projects looking at interactions between vegetation, disturbance, and land cover change from a modeling perspective. So the motivation for a lot of the work in the group comes from this what I call the carbon problem. And so as I'm sure everyone here is aware of, CO2 is rising quite rapidly because of human activities. And so I just took this figure from today, so this goes up through September 2015 from the Mauna Loa data. And so you can see that now we're quite regularly surpassing 400 ppm of CO2 in the atmosphere. I can remember doing field work when CO2 was around 360 ppm and calibrating the LICOR to about 360. And so I think all of us have our own kind of stories about how important this change in CO2, the main greenhouse gas, is over the past few decades. Montana has a relatively large role to play in terms of the carbon problem. So about 10% of U.S. coal exports are coming from mines within the region, and so we often hear these trains coming through town at night, and so I like to think of these as the climate change trains. Methane is another significant greenhouse gas, and we're trying to understand a bit about the methane concentrations and their dynamics in the atmosphere. Methane is particularly interesting because we see this increase and then a plateau that started in the late 1990s, followed by an increase in 2007. And no one knows why there was the plateau and why there has been this increase, which presents a really difficult monitoring and policy challenge. So, going back to the CO2, the way that we try to understand the global carbon budget is by breaking up the sources of CO2 into fossil fuels and land use change, and then try to estimate the sinks of CO2, where we have the main sinks in the atmosphere, ocean, and land. And if we understand the budget perfectly, then we would have zero residual error from this rather simple equation. But each term in the budget has quite large uncertainties associated with it. And so just as recently as 2 weeks ago, the emissions from China's energy sector were reduced by about 10% because they found that the coal that China is producing releases less CO2 per unit energy than what was considered by the IPCC originally. One particularly interesting thing about the global carbon budget is that the terrestrial biosphere is offsetting the atmospheric growth rate by about 30%. And so, so what this means is that ecosystems are providing this free service by mitigating the rise of CO2 in the atmosphere. And so in green, we can see that the land acts as a sink, and we have this large interannual variability, and we also have a trend where the sink appears to be increasing. And there's been several studies in the past 3 years that are showing that the terrestrial biosphere is behaving in novel ways compared to kind of historical periods. So this recent work shows that this paradigm that high latitude systems are temperature limited, which is the basis for paleoclimate reconstruction from tree rings. So this principle of uniformitarianism is now shifting as we see that high latitude systems are becoming less sensitive to temperature and more sensitive to precipitation anomalies. And this is because temperatures warmed in the high latitudes, and so this climate limitation is becoming less important. We also see in temperate systems that there's been a long-term change in the water use efficiency of tree species. There's been about a 15 to 20% increase in water use efficiency over the last 100 years. And then we also see in semi-arid systems a long-term greening trend, which we can partially use to attribute to the global trend in increasing terrestrial carbon uptake. And this figure here shows the land sink for 2014. So this is new data, and we can see that in 2014 the land sink was even larger than 2011, which helped us understand semi-arid systems. So things are changing in a rather novel way. So because of this novelty of how the terrestrial biosphere is responding, I would argue that we need new tools, or as many tools as possible to do this. And so we work with ecosystem models. And the particular class of model that we work with is known as a dynamic vegetation model, or dynamic global vegetation model. And these models are fully prognostic, which means that we're using numerical equations based on first principles for the source restoration, carbon allocation, to simulate the demography and biogeochemical cycles of ecosystems. And so these models work across multiple spatial scales. They include various feedbacks, which we'll see in some of the presentations coming up. We can make them management relevant by providing information at the species level. But they're also constrained by computational networking limitations. So we've been lucky at MSU to have this new Highlight high-performance cluster be implemented over the past several months. And Highlight is, for computer geeks here, has 44 compute nodes, and each compute node has 16 physical cores associated with it, so we have about 1,400 cores. There's lots of disk space, which is shared across the university, but we're taking up quite a large part of that. And then in total, it has about 12 teraflops of computing power, which is not bad. And but in comparison, the number one supercomputer has 33,000 teraflops. So, but anyway, but it's a great resource to have for us to look at ecosystem processes with these models. So DGBM models have been in development over the past several decades, and they really tie together a lot of research that has come from socioeconomic models, plant geography models, physiological models, vegetation dynamic models, and biophysical models. And so they aim to synthesize kind of the current state of understanding of how ecosystems work. And I'm sure a lot of people in the room have expertise in each of these topics or multiple topics that could contribute to the development of the DGBM category. So, so with that kind of introduction, the idea is that the team are going to make 10-minute presentations associated with how we can forecast ecosystem responses to short-term and long-term climate trends and climate variability. And so Zhang will present on our large-scale modeling and give a bit of an introduction into how we use the climate projection data to run these models. Kristen Emmett will present on her work in the GYE, which is taking place at very high spatial resolution, at least for us, and looking at fire and climate interactions. Jared will present a new approach that he's developed to a couple catchment routing models with a DGBM model, so we can model changes in hydrographs. And then Katie Renwick will present some work on El Nino and how these models can be used to look at some of the short-term climate variability. So over to Jean.
Hi everybody. I'm a postdoc working in Ben's lab, and my study is at a large scale using DGBM, focusing on the mass emission estimation from natural wetland and wildfires. What I want to talk is first is the climate projection we are using. Because we all know that over last several years, the adaptation and mitigation policymakers they need climate future information to make a more to want to know how the regional and the global climate change in the future. So they carried out the crop modeling comparison project, same project for the and using a sample of global climate models to focus how the future climate looks like. And there we are using now there are a bunch of new generation GCM. You participate in the SIM5 experiment, and we want to know how this global projection should be regionalized, and this regionalized global projection is necessary for forcing the global vegetation models. So this is we have most of this SIM5 their experiment area is constantly driving, like forcing with the changing greenhouse gases, and it shows with like different future temperature change. And what we want to know is how this forecast for the future can represent the regional signal, regional warming signal. So some studies that carry out like a metric of a calculate of statistics for testing, evaluating the SIM5 model's performance. And this is this figure shows how each GCM's model participating in SIM5, how this performs, and how how well they capture the future for the Pacific Western U.S. So we want to know. So what we got is we know there's a systematic bias in the SIM5 models, and we need to do what we need to do is first is to bias correcting the systematic and bias in SIM5 models, and we need to let it match the baseline of our observations for the precedent observation. So there's three different downscaling approach for like doing this. First one is the statistical model, and the second one is like dynamic model, which is like using like a weather research and forecasting system for carry out like a regional scale to capture the regional climate change, which can consider like topographic ingredients, some stuff like this. And the last one is using like hybrid approach, both use this two approach to do that. And this is an example for downscaling RCPs. First, we need to calculate the anomalies of the future scenarios from the GCM's model output, and we need to get the information about the realistic regional signal of the weather, of the climate. We did the biospheric. This is on the right side. This is an example for what we did for the bias correcting and the downscaling. It shows that the temperature change, systematic bias in the Canadian GCM's model result has been minimized, and this is a comparison between the observation from DayMat archive. And what we did this bias correction on highlight and on this high computer cluster. For doing this, we are using like a computational, more like economical way, not instead of using the dynamic downscaling approach, because that is a very, I would say, it's a high computational cost. So it's we did for 106 GCMs and for different RCP scenarios, for air temperature, cloud cover, and precipitation, the major climate change variables. And this is a list of these models. And I forced this our DGVM model LPJ with this bias-corrected result. And this is a figure shows how we do the spinning up for running the model. We did two different spin up, and the last one is transient run for the reporting period for the future. And this is our bias-corrected precipitation for Montana. It shows that it have a slight increasing trend for under the business as usual, that which means is RCP 8.5 scenarios, and show the increasing trend. And for the mean temperatures have a more significant trend in under RCP 8.5. The temperature, the mean annual mean temperature doubled from the current days, like around 6 degrees to about 12 degrees. This is the ensemble mean. So yeah. And this is the cloud cover. It didn't change it shows that it have a slight decreasing trend because the higher is more precipitation in the future. And this is the annual NPP in Montana, and it had an increasing trend because the carbon dioxide fertilization effect. And this is I currently get involved in forecasting the future wetland area dynamics. It shows it changing because the more precipitation in the futures. And we calculate the mass emission from natural wetland in Montana. It also shows to have a very large increase in the future. So, but in general, my study is carry on like a cross resolution because I'm focusing on more like a global scale. So for Montana region, it only covers 180 degrees Celsius. So and we carried out the whole bunch of a series of ensemble that will make us have a better estimation of the future estimate and the uncertainties, codify the range of the uncertainties. So, but these still have limitations because we carry out a large scale. We need take a more detailed look for Montana and GYE regions at the for get more insight from that, because the GCM model I use is we using like the average individual for like plant function type populations, not like specifically for each different the plant functions. So that's what my other colleagues they're studying. Yeah.
I'm Kristen Emmett, and I'm going to transition down to a finer scale. So I just want to reiterate that Jen points out some of the limitations of using this higher resolution. So there's some processes that are very scale dependent. Disturbance and vegetation dynamics are amongst them. Within the western U.S., fire is the largest disturbance that drastically impacts the landscape. So here is showing, well, a photo in Montana of a wildfire, and I thought this shows kind of the whole picture of, it's not just impacting the vegetation, but we have feedbacks on the hydrology and also on the animals as well. On the left, we can see a plot of the total burn area within the United States, and this is using the monitoring trends in burn severity data set. I'm going to be showing that a few times in my presentation. And so it's from 1984 until 2013. So you can show that you can see that there's an increase in the total burn area across the U.S. However, this varies regionally. So if we zoom into the greater Yellowstone ecosystem, now I'm going to be representing it by square kilometers, and so the entire GYE is defined by U.S. GS hydrological unit is around 200,000 grid cells, and the formatting changed. In the center, you can see the boundary of Yellowstone National Park, and I think also here we can see the importance of the topographical gradient. So the shading from black to white is the elevation in meters, and so you can see it goes from about 600 to 4,000 meters just within the GYE. Now, of course, fire is a long history in the GYE, and I thought this quote was good because it says, the 88 Yellowstone fires were among the first in what's proven to be an upsurge in large fires in the western U.S. So the graph I showed earlier showed we do see this trend in the U.S. overall. Within the GYE, we have a spike from the 1988 fires, and we've had a few other large fire years, but nowhere on the same magnitude as 88. And this has to do with our feedbacks with vegetation. On the left, you can see the fire boundaries as spatially represented, and so that's again for 84 to 2013, and that's the boundaries just of the 88 fires. So over 30% of the forest within the Yellowstone National Park boundary burned that year. So looking into the future, there's been some projections about how fire regime is going to change for the region. In this study, they were doing a correlation between temperature and precipitation and then fires. So it's a pretty extreme scenario, right? So it's saying that by 2100, so the end of the century, we could see a less than 10-year fire return interval. So that means how frequently a particular area is going to burn. So my question is, well, how likely is this, and what's missing? So my hypothesis is that fuel accumulation and other feedbacks are going to limit this fire return interval. So hypothesize here that initially there will be some other high severity fires similar to 1988 that will decrease our total biomass. But over time, we're going to see fuel become a limiting factor to the system. And we may also see changes in plant community types from forested to more shrubland and grassland communities due to both the fire regime and the changing climatic conditions. So to address these questions, I'm using the dynamic vegetation model LPJ-GUESS. And so as has been introduced at the beginning, so we're representing physiological processes, so photosynthesis, soil hydrology, and then we can actually calculate different states of the ecosystem as total biomass. And I circled here the processes that are represented that really get to the impact of disturbance. So since through these mechanistic processes we have a constant state of the vegetation and the amount of litter and the soil water, we can calculate fire dynamics. So here I'm going to present doing simulations with a historical period from 1980 to 2012 driven by observational weather data, and then also forcing it with a rather extreme scenario of a 4-degree temperature warming and a 50% reduction in precipitation, and then the projected CO2 concentrations from RCP 8.5, and then starting in that 2013 and going to 2050. So very drastic, but just a demonstration of concept. The other unique thing about LPJ-GUESS is that we actually are defining age and size classes on the plant functional type, and you can even go to species level, so we can get to those stand dynamic. So fire model within LPJ-GUESS, calculating fire currents that it's required. There's a minimum temperature, a minimum fuel moisture, and a minimum above ground litter for fire to spread. The fire size is calculated using empirical relationships. So the plot on the bottom right is just showing the relationship between the length of the fire season and the fractional area burned. Fire severity has to do with the fire-resistant parameter that you prescribe to the different plant functional types or species. And then the emissions is using that amount of fraction of biomass destroyed and then calculating the reduction in carbon from the different carbon fuels that are modeled. So leaves, sapwood, and heartwood for trees, and then leaves for grasses. All right, so some results. So this is for the historical period, and this is showing the year 2012. And so we're looking at the total biomass across the GYE and then the net primary productivity. So what I find interesting is we can see here the topographical gradient is pretty drastic. So we can see that in some of the higher elevation sites which are receiving more precipitation, so the orographic effect, we have places of up to 25 kilograms of carbon. If we look at carbon fluxes, so I was pretty excited about this. So this is simulated fire within LPJ-GUESS. So on the left we're seeing 1987, and the scale goes up to 5 kilograms of carbon per meter squared. So a little bit of fire activity in the west, but otherwise none. But then we see that 1988 extreme fire year where we're having up to 10 kilograms of carbon per meter squared burn. Now if I compare this to the actual measured monitoring trends in burn severity, the fire perimeters, we can see that it does a pretty good job of recreating the concentration around Yellowstone National Park. So now we're looking at the biomass and carbon flux through time. So the blue from here on out is going to be forced with that observational climate data, and then the red lines are going to be my extreme hot and dry scenario. So we can see that it's simulated that there's a slight increase in biomass and then a very extreme decrease, which perfectly correlates with the flux due to fire. And then we have another steady increase after that time and continuing the hot and dry scenario. But then the next hot and dry summer, we have again another extreme fire year on the same magnitude as the 1988 burn. Again, we have afterwards a recovery, but then after that time biomass declines, and this is due to the shifting the climatic conditions for the different vegetation. So this is why LPJ-GUESS is cool, because we can actually see the feedbacks with vegetation and on the plant functional type level. So this is the plot again of carbon and vegetation, the biomass. So we see those trends. The top is the total biomass. This one in green is using the plant functional type boreal needle-leaf evergreen, so evergreen trees, which you can see make up most of the biomass within the GYE. And the lower plot, this is biomass for C3 grasses. So we can see it doesn't follow the same exact trajectory. Instead, we see grasses are rebounding after those large disturbances. And then again here. But instead of the decrease, so now at the very end we have the super extreme 4-degree temperature and 50% reduction in precip. We see a decline in trees and an increase in our grasses. The plot on the left is just reiterating the change in that forest biomass So you can see it in some regions, and it's very spatially specific, a drastic decrease in biomass. All right. Is the timing good? Yeah, cool. Thanks.
So my name is Jared Hoy, and my project is on changes of hydrology in the GYE using outputs from the model that Kristen was running. And so some of the motivation from this figure on the right was from USGS and showed stream trends from 1970 to 2011. And you can see in the headwater area of the Missouri River Basin, it was mostly down overall. Some increasing down towards like Iowa. And the big thing is no one really knows why this is happening. But it's important because it has big effects on fish habitat, water availability, drought preparation as droughts become more frequent and severe in the future, and future climate change impacts will also have an effect on that. And so our objective was to attribute changes and stream flow to climate variability and trends and land use cover change, and water management by developing a stream routing model to pair with the LPJ-GUESS model. And so the LPJ-GUESS GGBM simulates a pretty full suite of hydrologic processes, simulates snow accumulation, rain interception, transpiration, and some of the outputs of it that we use are surface runoff and subsurface runoff. And so these hydrologic processes are coupled with vegetation and land use and the different processes that affect that. And it's kind of similar to how models like the VIC model, the Variable Infiltration and Capacity model, and Mark Monetto's ECHO model work. And so now currently in the model, water just leaves a grid cell and disappears. And so we developed a catchment-based routing model to try and route this and see those changes. And so LPJ-GUESS outputs surface and subsurface runoff at a monthly or daily time step. Here we use monthly time steps just to speed up computation time. And the graph below kind of shows those different hydrology outputs that LPJ-GUESS gives. And so the first thing we did was developed a stream network. So we used a 1 kilometer condition digital elevation model, flow accumulation, and direction rasters from USGS hydro sheds. And then we used RCPS and the ARC hydro tool to delineate the catchments and stream network using a 4.5 kilometer flow accumulation threshold, which seems standard among USGS. And then we used Shreve order for computation order. And so here's a map of the catchments in the GYE. So total there's 14,380 catchments, total of 207,000 kilometer square area. And all the red dots are the different stream gauges that we use. And so here's the river network map. So yeah, then there's a 1-to-1 ratio between catchments and stream segments. So total it was like 55,000 kilometers in length, and there's 167 stream gauges there that we get data for. And so some of the key assumptions of the model we made were that runoff generated in the catchment would enter the stream throughout the time step uniformly and uniformly throughout the length of the reach. And then so Q out comes out evenly from each reach uniformly, and Q in comes in. We use rectangular stream dimensions, base the width of the streams off an empirical relationship between contributing area. Height is just calculated from the storage in the river and the length and the width. We use Manning's equation to calculate velocity. So the routing model we use just kind of simple calculation of travel time through the reach. The first equation is the conservation of mass, and so we're trying to conserve mass through it. Some models don't, some do. The Q loss, we just set it to 0, but we could calibrate it for stream bed infiltration, irrigation management, or anything. And then that first second equation has kind of a limit on it where if water can leave the stream faster than the time step, it doesn't conserve mass. So we made a second equation for that. We're storing subsurface runoff as groundwater, and then it discharges into the stream based on a nonlinear relationship. And we spin up that to fill up the groundwater. And then, so this is during the historic period of the model that was just using historic DayMet data. We routed the runoff and got pretty good statistics. The main statistic used is the Nash-Sutcliffe efficiency. And so for this one it's 0.73, and then the other RNSE and MSE are kind of variations on that are less I forget. Anyway, so that's for the historical period. For both of them, we got pretty good correlation, pretty good Nash-Sutcliffe efficiencies. And then this is for the hot and dry simulation that Kristen talked about. And so overall, we see a decreasing trend in stream flow throughout that. And then here's for some lower flow gauges, which we kind of had worse correlation with. And so that's for the historic period. And then here's for the hot and dry simulation. Again, just decreasing trends we see. And then so this is for total or mean annual flow. And so we're generally kind of over simulating the flow. Then overall we see like a 50% decline in annual discharge through the hot and dry simulation. And so, I got my stuff on that a little bit. So future developments. So we're trying to improve the vegetation processes that affect hydrology, such as transpiration, rooting depth, water use, the different hydrologic processes. We're going to calibrate for the base flows and attempt to improve the snowmelt model that's with that. And then simulate management such as dams and reservoirs or timber harvesting, and improve the fish processes. And so this graph on the right shows RNSE, which is the relative Nash-Sutcliffe efficiency versus mean annual discharge. And it's just kind of showing that our NSE, the model performed better when the discharge was greater, when there was more flow to stream, and worse when it was less. So we're going to focus kind of on those lower discharge streams for further improvement. And yeah, thank you.
All right, so much of the work in our lab group is focused on these sort of long-term predictions and trying to look at how vegetation and other related climate patterns are going to change in the future. But I've done just sort of a little example here to look at forecasting 1 year in advance, just looking at 2016 and trying to see what we can learn about potential impacts of El Niño from that simulation. So El Niño, I won't get too much into the science of it, but basically it's related to sea temperature in the Pacific. And when we get this sort of shift in the warm area, it affects the circulation patterns over the Pacific Ocean, which in turn can affect temperature globally. So for the US, we would expect that in El Niño years, the northern portion tends to be a little bit warmer and drier than in regular years, while as the southern US tends to be a little bit wetter and cooler. Based on the forecasts that are coming out from NOAA, it's looking like globally 2016 is likely to be the hottest year on record. These maps are just showing the winter forecast, so December through February, from NOAA for temperature here and precipitation on the right. Looking a little bit more closely at Montana, this is an area that's expected to be warmer and drier than usual. So my real question then is, what are the implications of these shifts in climate, short-term shifts in climate? Might we expect there to be less snowpack, lower productivity in the vegetation, and potentially more fires next summer? And then also, how does that impact very spatially? The projections that come out of NOAA are very generalized with these sort of northern versus southern regions, and I was interested in looking at more of the fine-scale patterns within those general projections. So I've done that using LPJ-GUESS, and what I've done is to take this year, 1997, which is the strongest El Nino that we have in recent history, and so the closest analog to the projected 2015 to 2016 El Nino event, and use that climate data from 1997 to 1998 to look at what might happen in the coming year. So I ran LPJ-GUESS with the regular spin-up and historic climate data from 1901 to 2014, and then I replaced 2015 and 2016 with the temperature and precipitation data from 1997 to 1998. So this is just taking a quick look at the climate drivers for that model, temperature and precipitation specifically. And we can see that the general trend for temperature is similar to this forecast from NOAA, that we're going to have above average temperatures throughout much of the northern US, potentially. But there is a little bit more spatial variability that shows up in the LPJ-GUESS version. Precipitation, I think, is even more complicated in terms of these slightly different patterns within the general expected zones of warm and cool versus warm and dry that we get from NOAA. So the more interesting part, though, is how does that affect everything else? Looking first at snowpack, which is calculated in LPJ-GUESS based on a combination of the temperature and precipitation driver data, we can see that for the winter period, so December to February, up here, LPJ-GUESS is forecasting a reduction in snowpack below the average throughout much of the western United States. But again, there's a couple of spots in here where things aren't quite following the general trend for that region. Looking at spring, so March to May, the pattern gets a little bit more complicated. But the main point that I wanted to make with this is that what we would expect for at least the northern United States is warm and dry conditions means less snowpack. And that is what we see, particularly in the winter months when the impact of El Nino is strongest. But it's not spatially uniform. We do get these little pockets where it looks like there might actually be above average snowfall and snowpack. I think the time series is actually more telling for this. So here I'm taking data just from the state of Montana, and these lines represent each grid cell in Montana, looking at snowpack variability, so how different it is from the mean in each year over time. And I just highlighted two locations for the sake of being able to distinguish some of these lines. I did Bozeman here and then a spot in the middle of the Kootenai National Forest. And you can see that in these El Nino years, marked by the blue lines, there's still quite a lot of variability within the state of Montana. And I think that's most obvious here looking at the projection for 2016, where all of those gray lines, some are below average, some are above average. Bozeman looks like it might be maybe slightly above average, but not drastically so, whereas that upper northwest corner of Montana, it does look like the snowpack could be considerably below average. Looking more at how this might affect vegetation moving into springtime now, so looking March to May, these plots just show net primary productivity and leaf area index, which are two measures of productivity. And what we see for Montana in the sort of northern area here is actually what looks like above average productivity. And what I think is going on here is that you might think warm and dry plants aren't going to do as well. But in areas like Montana that are pretty far north, we have a really short growing season. So having warmer temperatures could mean an earlier spring and potentially more growth for plants during that 3-month period. But how does this translate into impacts on the fire season? This, again, is a plot showing carbon flux from fire over time. These are absolute values, not deviation from the mean. And the first thing that should jump out on this graph is just the 1988 fire season, which, like Kristen showed, this is simulated fire, so not actually actual data. But the model does show a big spike in fire emissions for that year when we did see large fires. Looking at El Niño years, 1998, there's not a huge increase in fires, and that, again, corresponds to the historical record for Montana. But in that year, we had just burned a large portion of the state. So that's where the vegetation feedback comes in that can be picked up in a model such as this. Looking at 2016, so this coming fire season, again, there's a lot of spatial variability, and it's really hard to say anything about a specific location, but it does look like there might be a slight increase in fire activity based on these slightly warmer, drier conditions that we are expecting. But to end with a little bit about uncertainty, none of these are to be considered exact predictions. There are a couple of different ways to do forecasts for El Niño. NOAA takes an approach where they're averaging over every El Niño year since 1950 to get some idea of the probability of having above average temperature. Whereas what I've done is what I would consider a snapshot approach, just taking this one El Niño event that we think is kind of similar to what we might expect this year to look at some of the potential impacts on vegetation, fire, snowpack, and also get at some of the spatial variability that gets, in a way, sort of averaged away with the NOAA forecast. And for all of you who are really interested in El Niño, just from the perspective of how will it affect the ski season, I'll leave you with this different forecast from the Farmer's Almanac, which suggests that it might be very snowy in Montana, but I don't know where that data comes from, and I suspect it's really just wishful thinking. So, with that.
Okay, so so to summarize, hopefully we've kind of given a survey of the different approaches that we're using in the group, using these process-based ecosystem models to look at short and long-term climate impacts on ecosystems. And so, I'll just to save time, I just leave this up here. I think we have like 5 minutes or so for questions or discussion. So, thank you.
So then we're showing that across Montana, precipitation
Right.
and then there's this figure that Kristen was showing that the fire frequency without fuel load, so the frequency itself should increase.
Yeah.
So is this something just because of the there being spatial scale that things are operating, or is it that because their VPD is increasing?
I think it's probably just because the climate data were different. So with Jean's ensemble, he was using the CMIP5, and then with Christian's simulation, it was with this like idealized scenario of drought. But I think also the point is that even if we're seeing, and you've talked about this before, even if we're seeing a wetter climate and increasing temperatures, we could be seeing a much stronger increase in vapor pressure deficit. And so, and the model has this, so this is considered when we calculate things like evaporative demand and stomatal conductance, and so those kinds of feedbacks would be there. For fire, we're moving toward looking at relative humidity of the fuel load and things like this, and so there would be a VPD kind of effect through that. So,
question for Kristen. Does your model provide a probability it will be a large fire in Yellowstone?
Yeah, so So again, for this, and I think it gets back to Josh's question, for this presentation, I was forcing it with just an extreme scenario, not using the global climate model projections. But that is what I'm planning to do for my PhD research. So it would be able to predict those years, of course, with the level of uncertainty. And the other caveat I'll say is that I need to calibrate the model. So I need to compare it to other estimates of biomass for the region to see if we're on the right mark, because perhaps I think I'm probably overestimating biomass a bit for the GYE. Does that help answer your question?
I mean, there's a nice paper out by Karen Nelson's group at looking at kind of lags in fire, following fires, and thinking about things like fuel accumulation, feedbacks, and so on. So there's some nice opportunities to kind of look at the data and then run the model out over the next decade. And one issue that so all of the results that we've shown are essentially with potential vegetation, and so we're not initializing the models with current land use and land cover and disturbance history and stand age structure, which could be done, but it's currently not incorporated here. Yeah.
So, one of the issues with so many GCMs out there is
right.
There's, you don't know which one to pick, and so we have higher confidence in the ensemble averages.
Yeah.
But then you lose all the kind of day-to-day and month-to-month variability.
Right.
So when you do replication, how do you get that variability back in? Do you have a weather generator that you have as part of the models, or are you using GCM daily output? Or?
Right. Yeah, I think we see the variability. So if you take the full ensemble and you take calculate the ensemble mean, then you lose a lot of the extremes or the variability. And so we're actually running these models with the individual GCMs to avoid that problem. And then, so the idea is that we would run either the full ensemble like Jen showed, or a subset, which is what we'll likely do for the GYE. And then I guess the art is in how do you take the spread and develop some kinds of probability surfaces and so on to communicate the impacts. But we're avoiding using our ensemble mean to make sure we have that variability there. So yeah, Rob.
A lot of your hydrologic characterizations do focus on volume of water. Do you take on account the timing of snowmelt as a potential hydrologic driver?
Yes, Jared's the expert.
Yeah, so the timing of snowmelt is simulated there. So the surface runoff that we were using to route was, and it's rain primarily generated from surface runoff. From snowmelt.
Yeah, so it's running on a daily time step, and so we have snowmelt produced on a daily time step.
I guess I was thinking in terms of that being an independent variable to another thing, fire. Is the driver behind fire is more tied to the timing of snowmelt than it is to the volume?
Yeah, roughly speaking, it would be, yeah.
So, I'm just curious if you're accounting for both timing and volume. What's the actual root cause of these types of?
Yeah, we have, with the hydrographs, we were really surprised and happy with how well they're doing at this level, but we think that the first thing to look at is the snowmelt and snow accumulation module. We don't have snow aging processes or erosional processes of snow included, and I think just getting some of that information in would be really useful.
And by the way, getting snowmelt right and getting base flow wrong is basically the result of any watershed modeling effort. So you're on the right track.
And another question about the 3 to 6 month projections.
Right.
I have a kind of an intuitive idea of kind of skill in those projections, but I was very intrigued by the spatial variation.
Yeah.
And I'm wondering how much skill is there in getting the spatial pattern right in a given year? Or is it just kind of we know there's going to be spatial variability. If we run the simulation one time, we'll get a certain pattern. If we run it a different time, we'll get a completely different pattern with about the same amount of spatial variability.
I think, well, we had done some other work just looking at correlations between the MEI inflow index and Snowpack at the 50-kilometer scale. So there we could kind of generate the spatial variability in snowpack anomalies. But for the work that Katie showed, I think the point of how you think about the spatial variability and the impacts is really critical.
Yeah, I mean, I would say I don't have a ton of faith in the spatial patterns. Like, I would not pick out a point of a ski resort and say, oh, cool, that looks good. But just sort of the general overall impression of trends for Montana, trends for the western U.S., and then also the degree of variability, I am a lot more confident in, and I think that's interesting in and of itself.
All right, well, thank you very much, man.
Okay, yeah.
Thank you.